Okay, so I'm Eliad. This talk is based on the joint work with Iftach Heidner, Noam Mazor, and Jad Silbach on the complexity of two-party differential privacy. So let's start with a very quick recap about privacy. So usually the setting is that we have a mechanism M that gets as input a database X, computes something, and we say that M is differentially private if the output on neighboring databases X and X prime is almost indistinguishable. Usually we capture this indistinguishability loss by epsilon delta parameters, and formally we say that M is differentially private if for every event H over the outputs, the probability that Mx is in H is epsilon delta close to the probability that Mx prime is in H. So let's see a very basic simple example. Suppose that Tel Aviv University wants to publish the number of workers that suffer from high blood pressure. So we can think about the database X as a binary database where Xi is 1 if the ith worker suffer from high blood pressure. So we are interested in the sum of the Xi's, and usually the way to privately estimate it is by adding some noise. And we can, for achieving epsilon differential privacy, we can just use a Laplace noise of magnitude 1 over epsilon, namely a constant noise. So actually what we describe now, very briefly, is the centralized model. M, the mechanism M has access to the entire database X, and usually the goal is to estimate some function over the database while preserving privacy. So in this talk, we are going to focus on a different model called the distributed model, and in particular, the two-party case that we will describe in the next slide. So what is two-party differential privacy? So in these settings, we have two servers, A and B. A holds the database X, and B holds the database Y. Now they interact with each other according to some protocol in order to estimate some function over the entire data X and Y. And the goal is to estimate fxy while preserving epsilon delta differential privacy. What it means is that in order to protect, for example, the privacy of B, we require that for every, no matter what database X A holds, for every neighboring Y and Y prime, the view of A in the execution pi xy should be epsilon delta indistinguishable from the view of A in the execution pi xy prime. What the view of A is basically whatever A learns from the interaction without loss in generality. You can assume it's the input random coins and the transcript of the execution. And the same thing, in order to protect the privacy of A, we require the same thing with respect to the view of B. Okay? Okay, good. So let's see a simple example. So suppose that again we want to estimate the number of workers that suffer from high blood pressure, but now the situation is that we have two different faculties, and each faculty wants to protect the private information from the eyes of the other faculty. Still, in this case, it's easy because the first faculty can just add noise to the sum of the xi's, and the second faculty can just add noise to the sum of the yi's, and they can agree on the sum of these two estimations. So basically, this approach, we can think for every functionality that can be written as something like f1x plus f2 of y, we call it modular functionality. The task is basically as easy as in the centralized model, but it seems much harder in the general case. For example, what can we do if the functionality is the inner product between x and y? Okay? So the inner product is a very important fundamental two-party functionality because it measures correlation between databases. So suppose that A holds a database of some population, whether they are smokers or no. Let's say 1 is a smoker and -1 is not a smoker. And B holds the information about this population of the high blood pressure information. So estimating the inner product between X and Y is basically estimating whether there is a correlation between smoking and high blood pressure. So now the question, can we do it in a two-party case? So regarding upper bounds. So basically, using techniques from the local model, using randomized response, that basically A just sends a randomized version of each of the xi, we can do it. And it will lead to an additive error of square root of n over epsilon, just because of the randomized noise in each coordinate. And actually, if we want to focus on utility only for uniformly random databases and xy and not for every xy, we can just even do something much simpler. We can just output 0. The parties can output 0 without any interaction, and this will lead to an error of square root of n, just because the inner product of two random x and y is going to be something like square root of n. But note that in the centralized model, we can achieve a constant error, 1 over epsilon error, for every xy, independent of n, just by adding Laplace noise to the inner product. So this leads to the following question: is there a more accurate two-party DP IP protocol? And IP in this case, we are denoting IP as the inner product in all this talk. Okay? So it turns out that there isn't. There is a lower bound by McGregor et al., which states that for every protocol, every epsilon delta DP protocol pi, the additive error on the respect to the inner product must be at least square root of n over log n, okay, for uniformly random databases. Basically, this means that up to this log n factor, the protocol that just output 0 is the best thing we can do. So that sounds bad. So let's, so researchers thought about a relaxation of the definition to the computational case. So here is an equivalent definition that we saw in the first slide. So M is epsilon delta dp if for every neighboring x and x prime and every unbounded distinguisher d, the probability that dmx is 1 is epsilon delta close, the probability that dmx prime is 1. Okay, this is exactly an equivalent definition, but using this view of the definition, we can define a relaxation of it by considering only a efficient d. So we say that M is epsilon delta CDP, and here CDP is computational differential privacy, not concentrated, okay, in this talk, so don't confuse. So we say that M is epsilon delta CDP if the above only holds for a PPTD. Namely, an unbounded D might be able to distinguish between MX and MX prime, but an efficient D cannot. Okay, and we denote this indistinguishability by this superscript C. Okay, so now we have a relaxed goal. We want to do two-party CDP, and the relaxed goal is to estimate some functionality while only preserving epsilon delta CDP. Okay, where we want only the indistinguishability, the views will be only computational indistinguishable and not information theoretic indistinguishable. Okay? Okay. So it turns out that under cryptographic assumption, we can basically do whatever we can do in the centralized model. Because now, using cryptography, the parties can just simulate any centralized mechanism that they want using a secure multi-party computation. You can think about this as such a protocol that they don't understand anything except of the output of the execution. So we can just simulate a centralized mechanism. So if M is a centralized epsilon delta dp, then the protocol is epsilon delta CDP. And secure multi-party computation can be done using public key cryptographic primitives, and in particular some primitive called oblivious transfer. Not that important what it means. And for computing the inner product, the basic means we can just simulate the mechanism that adds Laplace noise, and that's it. So using oblivious transfer, we can construct a very accurate CDP protocol, like in the centralized model. And this leads to the following questions that we are trying to understand this work. What is the minimal complexity assumption needed to separate between distributed DP and CDP? For example, in the inner product, so we need to assume something because we know we cannot do it information theoretically. In particular, we can ask are one-way functions, like the most fundamental cryptographic primitives sufficient, or maybe public key crypto like oblivious transfer is necessary to do that. And even if public key crypto is necessary, do we have to use like a heavy secure multi-party computation? Because in general, secure multi-party computation can be very expensive. It doesn't require like one OT call. It requires many OT calls, and usually it's highly impractical. So I guess as many of you does not understand all the cryptographic primitives. So let's see just a picture of what is happening here. So basically, a very high-level view of crypto. Like we have two main worlds. Like there is the secret key crypto world and the public key crypto world. So in the lower part, the secret key, like the most fundamental primitive is a one-way function. And we know that it's equivalent to many other primitives that we know, like pseudo-random generators, pseudo-random functions, commitments, and other things. And in the public key crypto world, much less is known. Like the most basic primitives are key agreement and above it, oblivious transfer. So the goal is to understand what is the place of this non-trivial distributed CDP. So what I mean by non-trivial distributed CDP, it's some protocol that achieves some kind of accuracy that is possible to do it using the computational relaxation, but is impossible to do in a two-party DP, in the information theoretic case. Okay? So basically, we know that we can do it from OT by secure multi-party computation. And we know also that if the non-trivial accuracy is achieved for noticeable part of the input, it can also imply the one-way functions. So now the goal is to understand what exactly is the place of this box. So there are previous works showing that if the database, if you have two parties and each party holds only a single bit database, and the goal is just estimating, let's say, the XOR of the two bits, so doing something better than trivial basically implies OT. Okay, but actually for a single bit, it's not that interesting in the context of DP because DP is usually talking about large databases, and even in the centralized model where you have just a single bit, the error must be large. So it's more interesting to understand what happened for functionalities of large databases, and in particular, non-trivial CDP IP, where the functionality is you have large databases and you want to estimate the inner product. So again, we know that we can do it with oblivious transfer. We also know there is a result by Heiner and I showing that you cannot do it in the random oracle model, and thus it basically means that you cannot do it in a black box way from one-way functions. And actually our result is we show in this work that this box implies key agreement. Namely, public key crypto is not only sufficient, it's also necessary for this task. And really the place of this thing is the public key crypto world. So let's see our main result, the statement. So any epsilon delta CDP protocol pi that for some additive error L satisfies that the confidence of this additive is sufficiently larger than L over square root of n. Let's say you think there is like a missing constant here, like a million, okay? So any such protocol can be used to construct a key agreement. So it looks like a little bit hard maybe to parse it, but let's just think about concrete values. Let's think of epsilon as a constant, and L is something like square root of n over a million. So what we get here is that if we have a protocol that on uniformly random xy has error square root of n over c, even with only 0.01 confidence, such a protocol implies a key agreement. And note that this is tied up to a constant, because if you think about the trivial protocol, just the part is just output 0, this zero protocol has the property that for every L, it will give you a confidence of L over square root of n. Okay, this is like the probability that the inner product just will be with distance s is L over square root of n just by the properties of the binomial distribution. Okay, so what I tell you, if you replace this L over square root of n just by million square root of over square root of n, then this is become not trivial, and we can do it from it a key agreement. Okay, and in some sense, so basically a nice also thing about this result, it improves the impossibility result of McGregor et al. In the information theoretic case. And it also has a log n improvement because here we have a square root of n and not square root of n over log n. Okay, in order just to understand why it gives us that. So suppose that we have an information theoretic protocol that has, let's say, such kind of accuracy. Then using our theorem, we can construct for it information theoretic key agreement. But the latter does not exist. And so we conclude that such a protocol does not exist either. So in order to prove it, basically we need to do a reduction. We need to take an accurate CDP protocol for estimating the inner product and to construct from a key agreement. Okay, so basically a key agreement is some kind of protocol that two parties agree on something, where a third party that just see the interaction does not understand. Okay. Okay, so this is the construction. So Alice chooses a random x, and Bob chooses a random y, and they apply the CDP-IP protocol and get some estimation of the inner product of x and y. This denote this by out. Now, Alice chooses a random string r and sends xr, which is all the places in x where ri equals 1. So basically, you can think that there are some kind of n over 2 indices that Alice sends, and up to rearranging, we can think that basically Alice sends the first half of her database to Bob. And Bob now sends y minus r, which is all the places in y in which ri equals 0. And again, up to the rearranging, we can think that Bob sends the second half of his database. Now, Bob can compute the inner product of xr, yr, and Alice can compute the inner product of x minus r, y minus r. And so Bob can compute it, and Alice, using this inner product, can estimate the out B just by using the estimation of the box. So she used the estimation, she compute out minus the inner product of x minus r, y minus r. So just to understand what is happening, so suppose just think that this out is exactly the inner product. What the protocol gives us, let's say it's equal to the inner product of xy. So in that case, what Alice computes here, when out is just the inner product, is exactly equal to out B. Okay, just by the linearity of the inner product. Okay, so regarding analysis, so agreement follows from the fact that if the output is close to the inner product, then we really get that the out A is close to out B. The parties agree on something which is close. And regarding secrecy, so we need to claim, so this is like the second property of key agreement, we need to claim that for every PPT if that only sees the interaction of the parties, okay, what is the interaction? Is the transcript of the execution of the protocol, this r, x, r, and y minus r, it must be far from out B, which is the inner product of xr, yr, okay? If we can prove that, then we have a gap, and this will lead to a key agreement. Okay, so what is the intuition? Why this should hold? This should hold since if you can think about this process. So we entered some uniformly random xy to the box, and so condition on the transcript, those xy still become unpredictable by privacy. This is just by the privacy property. You can show that each bit condition on the other bits should be highly unpredictable. And therefore, basically, what Eve sees, it sees the XR, it sees the Y minus R. So we want to claim that because Eve doesn't see YR and it doesn't see X minus R, then she cannot compute the inner product of this part and not of that part. This is what we want to claim. But this is a little bit subtle, it's not that simple, okay? And we really need to use the fact that this R is random, because if R wasn't random, let's say I fixed this R to be the first n/2 indices, exactly like in the picture. Then I cannot claim that this holds, because maybe, I don't know what the protocol here in the transcript reveals in addition to the inner product. It might also reveal an estimation of the inner product of the first n/2 indices. Okay, it might also happen, but we want to claim that for a few hours it might happen, but for most of the hours it cannot. So if we choose a uniformly random R, we really get some kind of secrecy. And what we are proving is that if we think about all these processes as random variables, so we prove that condition of this transcript, condition on T, R, XR, and Y minus R, this inner product, the out of B, has a high mean entropy. Okay, and this leads us to basically proving the gap, the secrecy property. This is enough. But because we are in the computational case, it's not enough just to claim that we have high mean entropy. We also need to give a constructive proof. Namely, if there exists some Eve that predicts this XR too well, then we somehow need to efficiently reconstruct using it some coordinate of X or Y. Okay? And this is what we are doing. And just again, this is not exactly a key agreement, but this gap between agreement and secrecy can be amplified into a fully secure key agreement like in the literature. Okay, so regarding main challenges. So first is doing some kind of a reconstruction attack. So suppose I give you a database and some access to a non-trivial estimator, Eve over that you give it R and you give it the statistical linear statistics ZR, okay? And by non-trivial, it just means something better than 0. That for some L, it gives you a confidence of, let's say, 1000 L over square root of n instead of just L over square root of n. Then the goal is to construct a PPT algorithm rec that for most of the indices, let's say 0.9 of the indices, if you give it all the other indices, it can construct the ZI, okay? This is like the first challenge, and we are doing it in the paper. It's using n-cubed random queries to Eve. But this is not enough, because actually what's happened in our case is some kind of a C-dependent leakage. So in our case, you can think that this Z is basically the product of X and Y of these two databases in each coordinate, and coordinate Y is the product. And we are given not Eve that give it R and she gives you the R. You also need to give Eve the XR and Y minus R. Okay, so it's a weaker Eve. Okay, this Eve guarantee only accuracy when you give it the correct value of XR and Y minus R. So, for example, I don't want to do a reconstruction. Let's say that I have all the bits except of this XI. So I cannot call, so I want to apply the reconstruction attack. I cannot call it on R's where Ri equals 1, because in that case, I need to give Eve also the value of Xi. And maybe if I will give it the wrong value, it will give me a wrong answer. Okay, and this is like the main challenge, and it took us like half a year to understand how to handle this challenge, but eventually we have a very nice solution for it. So for summary, our main result is the non-trivial CDP-IP implies a key agreement, and actually we have a simple and shorter proof for the case that the confidence, if we assume that the confidence is really almost 1, we have a very nice proof. It basically means that in the challenges, we ignore the first challenge of handling the low confidence regime, and then we can do something much simpler. Regarding other results, so I talked about a new condensing theorem for unpredictable sources, the high mean entropy theorem. It's also called in the literature strong Santa-Vazirani sources, and things that are nice that has a seed-dependent leakage and constructive proof, which is makes it also interesting. And we also talk about efficient reconstruction attacking the low confidence regime that might have independent interest. And regarding other problems, so characterizing more functionalities. So we talked about the inner product, but understanding, let's say, what other functionalities, like what is a non-trivial accuracy for other functionalities, let's say even low sensitivity functionalities, what is a non-trivial accuracy and whether it implies public key crypto or not, it's completely open. It's also for, if we're focusing on the IP, is OT is necessary, okay? So actually our result is tight for a weaker notion of CDP, called the CDP against external observer. So when we defined the CDP two-party protocol, we said that the indistinguishability should hold with respect to the views of each party. But if we only, if we make a relaxation of it, we only require indistinguishability with respect to the transcript of the execution, and not with respect to the views, then it's a weaker notion, and we show that this one implies key agreement is actually equivalent. So the lower bound still hold for the standard notion of CDP, but the upper bound is still OT, and it might be the right answer. And that's it. Thank you.